get to it. This Friday, party time, folks, we have a midterm. I did post on the week 4 a couple of things. One, practice quiz number 1A and also 1B. So there's 2 practice quizzes you can try. They are examples from previous years. Okay, and you can just try to solve those questions, see how it goes. And then I think on Wednesday night, I'll post the key to those 2 practice quizzes, so you can see if you did it right or not. I highly recommend that you try those questions before you look at the key, because otherwise you will be missing a great learning opportunity. Also, there is the so-called examples for bracket notation. Okay, that's the thing that we kind of talked about last Friday. This very awkward way of writing things, integrals, but it turns out, when you get used to it, very helpful. Okay, so make sure you look at those examples. And also the worksheet this week contains some examples of bracket notation as well. So make sure you look at all those things before the midterm quiz comes along on Friday. Are there any questions about the logistics of this week? Things you feel uncomfortable about? Everybody's in a good mood. That's fantastic. All right. We should have a midterm every Friday, you know. If you guys like it so much, can be done. Just let me know. There is, however, so I'm glad you guys are here, okay? Because there is homework this week as well, so it's a little unfortunate. So we have a midterm, and then on Sunday we have homework. We have to do that to just stay on track, okay? So don't get mad at me, please. It's for your own good, okay? So don't forget to do homework for week 4. Okay, so we talked about a lot of things already, and we are inching closer to our goal of describing the electron in the atom. And one of the things that we will come across if you talk about an electron that is part of an atom is that there is some sort of circular symmetry to an atom, okay? The atom has no sharp edges or, corners, and therefore the circular pattern is something that we have to contend with, okay? So we'll start there. We'll start with basically a ring, which is a circle, and we say the electron moves on that ring, okay, or is on that ring. That is a good step towards our atom. So because we can think of the nucleus as sitting somewhere in the middle of that ring, and the electron swirling around, okay? It's not exactly complete, not a perfect picture, but a good starting point. Now on Wednesday, we will try to kind of make that a little bit more explicit by not just looking at the ring, but actually the entire sphere, okay? That's a 3-dimensional, more like a 2-dimensional distribution because it's a sphere, so it's the surface of the sphere, and we'll try to see what the electron does on that spherical surface. But right now, let's talk about the particle on a ring. So, what do we have? We have a particle, and we'll start in a very simple way, and we'll refine the meaning of this as we go along in this lecture. So let's for now assume that the electron is a little point, that green point over there. We know that's not exactly correct. We shouldn't think about a point source that moves around like that, okay? But rather like a wave that happens to be there. But for now, let's just assume that the electron is a little point that swirls around. Then what? How do we describe that? Okay, so the point, if it is fixed on a circle, at all times has a distance r to the middle of that circle. So the r doesn't change. I hope you agree with that, because that's the definition of a circle. And the thing is going one way, let's say. So it just swirls around. In this case, it goes kind of counterclockwise. Okay? So how do we describe this? Classically, and then quantum mechanically. So let's compare that. Okay, so let's say the mass of this particle is m, the mass of the particle is m, okay? And in translational motion, then m is just the mass, and it's just something we are very familiar with. But it turns out, in rotational motion, a better descriptor of the mass is actually the moment of inertia in terms of angular motion. Okay? The angular moment of inertia is called I, which is m times r squared, where r is the radius of the circle. This is a little different. And you will see in a few moments why we kind of equate the mass in translational motion, so x, y, z motion, linear motion, with the I in rotational motion. So for now this may look a little weird, but you will see that I is taking on the role of m that m was playing before in our Hamiltonian, okay? You'll see it pop out. Momentum. What is momentum in linear motion? That is always m times the velocity along x, y, or z. And in rotational motion, that's a little different, because we will call that the angular momentum, and it has a letter assigned to it, which is an L. Okay? Lowercase l. And lowercase l equals I, the same I as above, the moment of inertia, angular moment of inertia, times omega. Omega is the angular frequency. Okay? That's how many times it goes around, how many radians it goes around per second. That's what angular frequency is. So it looks a little different. Kinetic energy, we know what that is. Kinetic energy in most general terms is the momentum squared divided by 2m, and that corresponds to half times m times v squared. So what does it look like for rotational motion? It looks like half times I times omega squared. I'm doing the same thing. Little l squared divided by 2I equals half times I times omega squared. So what do we see? We see a couple of things. You see indeed that this m in translational motion is now replaced by an I. So I takes on the role of m, so to speak, and omega takes on the role of v. Okay? So velocity is going like zip in one way, and the angular velocity is going around the circle. Alright? So, and this, all of this is just classical stuff. There's no quantum yet. Okay? So let's pour in a little bit of quantum mechanics. So, what are we going to do? Well, if we talk about quantum mechanics, we would like to find a wave function. And if we want to find a wave function, we have to find the Hamiltonian first of this particle. So let's do that. If we design our Hamiltonian, we have to, of course, look at our system and say a few things about it. And so what I'm going to say is that if the particle moves on the circle, it will not find any obstruction. So it can just freely move around the circle. There are no potential barriers on that line. Okay, so V equals 0. Good. So it is moving, as you can see, in the plane xy. Okay? It's not moving in the direction z because it's confined to the xy plane, but it's confined in the circle. So in the most general terms, I can just write the Hamiltonian as basically the second order derivative with respect to x and the second order derivative with respect to y, because it's a two-dimensional, just like a two-dimensional box. There's no potential energy, so V equals 0. That's good. And then try to solve this. But this is a little inconvenient because this doesn't quite describe the circle automatically. And so it would be much better if I convert my x and y to polar coordinates. Alright? R and V. That's the proper way to do it. Because R is fixed and only phi changes. So instead of having two dimensions, I will only have one dimension, which is the phi angle is the only thing that changes. So that's what I'm going to do. Now, luckily for us, we don't have to do it on our own. Okay? I'm going to basically just do that. I can do that if I really have to. But I will just look at the book and say, hey, what is the second order derivative in polar coordinates? And then the book says, here you go. Whatever is in parentheses, that's your answer. You can certainly prove this, but we will not waste our time on it because we want to focus on the physics here. So what does it say? A couple of things. So the only thing I've done so far is I've rewritten whatever is there in parentheses now in polar coordinates. And I see, instead of 2 terms, I have 3. Is that problematic? Do I make things worse? Not really. Because look, the first 2 of these terms depend on r. A change in r here, and a change in r here. But r is not changing, because r is constant. So the first order derivative and the second order derivative are both 0 for something that doesn't change. There's no derivative. Right? That means that both of these are basically 0, and I'm only left with the last term. That's good. That makes things easier. So what I'm getting is this. I only keep the last one. And of course that one only depends on phi. That's what I want. So that's what I did. Now the funny thing is, as you can see, this 1 over r squared that sits there now sits here. And I notice this mr squared. That is I. That is my moment of inertia on the circle. There's an I again. So my I sneaks into my Hamiltonian. This is what I'm getting. 2, not 2, well there's a 2 in there, but let's start with h bar squared over 2I. Previously there was m, remember? H bar squared over 2m, but now it's 2I. So I has taken the role of m. And then, instead of x, I have phi. Because phi is the thing that changes. Not x explicitly, or only. So this is my Hamiltonian. Pretty simple form. Hope you agree with that. What is next? Well, next, of course, I'd like to see if I can solve my favorite equation, which is the Schrödinger equation. That means that this new Hamiltonian that we just put together is going to act on a wave function and then generates a constant, which happens to be the energy, times the wave function again. That's what I want. So I want to solve this eigenvalue equation. Can I do that? I think you can. So let's write down this Hamiltonian once more. There it is. Operates on my function to be solved. I call it capital phi. It depends on little phi. And then it should be generating a constant, that's the energy, times the wave function again. So this is a differential equation, one more time, saying that if you take the second order derivative of a function, you should be getting a constant times the function. Now, this looks very similar to what we did before. Okay? And I'm going to take the same steps. So you see that this prefactor that sits all the way to the left. Okay? It's basically this. I'm going to divide that out on the left and put it here on the right. And so what I'm getting then is this. We did that before. We did it before with linear motion, and now we do it with angular motion as well. So I get 2I times E divided by h bar squared with a negative sign in front of it. Okay, so this is the particle in the ring problem. Now, I'm going to show you what we did before. This is a few lectures back. We had this equation that we wanted to solve, which is the second order derivative with respect to x, and that equals then, again, some sort of prefactor, 2me divided by h bar squared, negative sign. That was what we had last time. You can see, hopefully, that there is a lot of similarity. Phi has taken the role of x, and I, capital I, has taken the role of m, but everything else is the same. The mechanics of this equation is exactly the same, just a renaming of some things. So that is the particle in the box problem in a one-dimensional box. So I'm going to say, well, if the mechanics is exactly the same, the way it looks is the same, just renaming of variables, then the solutions also must be the same. Okay? So the general solution then is the same as before. Okay? Namely, I'm going to write this in terms of two complex exponential functions, one with a positive sign, one with a negative sign. This ML previously was called K, but now it's called ML because I want to give it a different name. What is this ML then? Well, it is this thing. Okay, and when you say, okay, what does it come from? Well, this is exactly the same as the K that we had before. The K was 2ME over h bar squared, and then the square root of the whole thing. But now I have ML, which is the same thing, except that now M is capital I, the angular moment of inertia. Okay, but you see that the structure of the solution is the same. The most general form of the solution is the same. Does it make sense? To some extent it does, because again, this is kind of quasi one-dimensional motion. I'm on a ring, but it's like one-dimensional motion. It goes on and on forever, because it's on a circle, but there's definitely some similarities there. So if everything is the same, are the solutions like the same across the board? And the answer is no, there are differences. And that's what we're going to look at right now. So let's think of this complex exponent again and write it out in this standard way, in terms of the cosine and the sine. And I do that because I want you to think about this thing as an oscillating function. So let's forget about this I sine and just focus on the cosine, the real part. The real part of this complex exponent is just a wiggly function. That wiggles is a function of phi. And so therefore I can just draw that and visualize it in my head. Remember, there's also an imaginary part, but I will just not worry about that now. We just want to have some sort of picture. I only focus on the real part. Okay, so here it is. I'm going to draw now this wiggly function on the circle, something like that. Right? Because this function goes up, down, and moves along the circle. So this is a good representation of the whole thing. And you can see now this is a wave. So this is a wave that's confined to a ring. Now what can I say about this wave? Well, I have to think about what are the conditions, what are the qualities that this wave function must have. One of these qualities is that the wave function cannot be multiple valued at certain points along the ring. That means it must have a single value at each point along the ring. It cannot have double values or triple. That's something that we did before. Remember that? Because it relates to finding a probability along the coordinate. If it has multiple values and there's multiple probabilities, that doesn't make any sense. So it must be single value. Well, that actually means something. And this is something that is a little bit different from the particle in the one-dimensional box, where we had clear points where the wave function must go to zero, namely at the edges. Here, we don't have that, because we don't really have a real edge. You see that? There is now suddenly a potential well that goes to infinity here. We don't have it. It's zero everywhere. But we do have this condition of the wave function must be single valued along the ring. And that means that if I take a given point phi on this ring, okay, here, and I go around in a circle, that it must end up at the same spot. Because if I don't, it ends up at a different spot, or different amplitude, and that means it goes around again and it traces different values. That means now I have multiple values for a given phi. That is not allowed. So in order to do that, I must have this condition. For a given phi, if I add 2 pi to it, so I go around a ring, I must end up with the same amplitude of my wave function. The same amplitude at phi. Okay? So at phi and phi plus 2 pi, I must be getting the same amplitude. That's why this must hold. So, if you look at this equality, inequality, what I'm going to do is I'm going to divide both sides by the right-hand side. Okay, that means on the right-hand side, I'm getting 1. And on the left-hand side, if I divide by that complex exponent, I'm actually I'm dividing out this phi part, and I'm only getting this term. Okay? So what I'm having, I have this condition. So what I did, the equation above, and the next one, I divided it by the complex exponent on the right. Okay? That's what I did. And then that's what I'm getting next. I'm getting this condition that this complex exponent, which says I times 2 times pi times ml, that whole thing must equal 1. Now, that is not so hard to solve, turns out, okay? Because that is actually fulfilled whenever ml is an integer. This condition is true. Whenever ml is an integer, including 0, positive and negative values, this is fulfilled. Okay, so this is kind of my quantization condition. Quantization condition doesn't follow from sharp edges, but actually from the kind of single value character of the wave on the ring. That's where it follows from. Here again is a sketch. If you don't fulfill this condition, then you get indeed multiple values at certain positions on the ring, okay? Because it doesn't trace itself back where it came from. It actually traces out a new wave, and therefore you get multiple values. And this is not allowed, okay? It must be single value. This is one of the key conditions that the wave function must abide by. Okay, so this is good news. I have now a condition for what the values of ml must be. This is my quantization condition. Okay, so what I'm going to write now, I'm going to write down the wave function, and I'm going to say my wave function is a, some kind of constant, times e to the power I ml, where ml must be an integer, times phi. That is my wave. There's also a negative one, but I'm going to now focus only on the positive one and see what I can learn about this function. The first thing I would like to know is, can I normalize this thing? Okay, so can I create an n in front of it such that this function is a normalized function? How do you do that? Well, the most general way to do that is, of course, you take the modulus square of this function, and then you integrate it over the entirety of the irrelevant space. What is that? Well, the irrelevant space is now, remember, polar coordinates, okay? This is polar coordinates. And in polar coordinates, if you are taking the integral over the plane, then you get r times d phi when r is constant. So you integrate over phi because that's a changing variable, but r is still there because the larger r is, the larger the ring, and so the longer the path, okay? So that r has to be there. That's what happens when you integrate in polar coordinates. Hopefully you remember that. So the integral over phi, the r has to be there in that integrand, and then I have between the modulus signs my function. My goal is to find n squared. So therefore, this whole thing must equal 1. That's the condition for normalized wave functions. Can I solve this problem? I hope you can, because the complex exponent, the modulus square of it, is what? 1. That's just 1, always so. And therefore, I just get the integral that looks like this. This r naught, r0, is just a constant which I can take out of the integral because I don't integrate over it, I'm only integrating over phi. And therefore, after I substitute the complex exponent modulus squared by a 1, I simply get the integral from 2 to 2 pi, sorry, from 0 to 2 pi, that's the total ring, okay? 2 pi around for phi, d phi, okay? So that's easy, because the value of this whole integral is simply 2 pi. That's the length of the circumference. Circumference is 2 pi. So it's just 2 pi. So what I'm having here is 2 pi r0, which is the radius, and then n squared, remember, must equal 1, and therefore I can find my n. My n equals 1 over square root of 2 pi r0. Pretty good? Yes?
Why didn't we factor in the a constant when we normalize?
Because I'm replacing a with n. I'm going to put a condition on what this a should be.
Okay.
I'm going to call it n now. Good question? All right, so here we are. Particle in a ring, normalized now. Okay? What can I learn from this wave function? Well, let's look at the probability of finding the particle somewhere in the ring. Remember, that will be the wave function modulus squared. That is the probability density. Okay? So we'll look at this. If you look at this wiggly function, remember this is the real part of the complex exponent, then you may think that there are locations where it is high, and there's locations where you actually have 0, right? And you may think that some places it's more likely to be than other places. But that's weird, if you think about it physically, because on a ring, there's nothing that says that it should be more here than here, because it's the same everywhere, okay? So it would make much more sense if the particle has an equal probability to be anywhere along the ring, because there are no things on the ring that break the symmetry. If I have a one-dimensional particle in the box, I have clear barriers that break the symmetry. Here, it must be 0, clearly. Here I don't have that. On this, I can walk on the circle forever and ever and see the same thing all the time. Why would it be somewhere a higher likelihood than in another place for the particle to be? There is no reason for it. And so I expect that to be the case. In order to prove that, I'm going to just determine the probability density. Okay? What is it? It's just this wave function squared, modulus squared. And that is going to be 1 over 2 pi r0. Okay? Seems like a silly result, but it actually is meaningful. It's a finite number, and it's the same everywhere. It's independent of phi. This probability density doesn't depend on phi. It doesn't depend on where you are in a ring. It's always the same. It has a constant probability density along the ring. And physically, I think that makes sense. This is different from the particle in the box. The particle in the box had real zeros, always at the edges, and sometimes in the middle or in certain places, okay? Because there the probability density was 0 because of the bending of the wave and so forth. But here we don't have that. We don't have it. It's the same everywhere. What is another property of the wave function has? Well, it has energies. And a general form of energy, we have actually a condition for this m. I can write it now in terms of energy because m depends on E. So I'm going to write E in terms of m. This is the same as we did before with k. Previously we had k squared h bar squared over 2m. Now we have ml squared h bar squared over 2I. That's a general expression for energy. What do I know about this energy? Well, I know that ml must be an integer, including 0 and including all negative numbers. Okay? Again, compare that with what we had before. That was linear motion, that is circular motion. You see the similarity, but there are differences too. Again, the probability density was different, and with energy there's also something different. What is different? Well, for instance, ML is 0 is allowed. ML is 0 is allowed. This is confusing. Why is it that the particle in the box, N cannot be 0, but ML here on a ring can be 0? If I substitute 0 in the energy expression, I get 0, meaning the kinetic energy of this particle on the ring is allowed to be 0. Isn't that weird? Didn't I make a big fuss about this last time? 0-point energy and so forth, and now suddenly it doesn't apply. Who knows what it is? What is the difference between a particle in a one-dimensional box and a particle on the ring? Why do you think that here, a particle actually is allowed to have kinetic energy 0? It has to do with the fact that there are no barriers. There are no barriers. Even though the particle is confined to a ring, on this ring, in this space, it can go on forever and ever and ever. There is no beginning, there is no end. Basically, it traces a one-dimensional infinite space. This is the same as saying I have a particle in a box where the barriers are at infinity. I can go on and on and on. Okay? In that case, there is no real condition that says that there must be a 0-point energy. The 0-point energy must come from confinement. True confinement, where I force something upon the wave function that kind of makes it such that the kinetic energy must be there because it must have a certain curvature to fit in that box. Here I don't have that. It is allowed, like a particle in free space, to have kinetic energy 0. Different from that of a particle in the box. Okay. Another property that this particle has is that it has angular momentum. If I think of this particle as going one way, it has a certain velocity, and if I'm assigning a velocity to this wave function, then it should have angular momentum. Okay, so let's look at it one more time. This is again my situation. Particles on the ring, it moves around, and I'm going to be concerned with one-directional velocity. So let's say at any point of phi, there's going to be an angular velocity. If it would be linear, I would call it p, but I'm going to go on a ring here. So I call it L. Okay? And L, the angular momentum, is defined always. This is, again, not quantum mechanics, this is general. This is also classical. L equals R, and then you see this X, that is a vector product with P. Okay? So all of these things are vectors. You have R, that's a vector, this P, which is a vector, and then therefore the angular momentum is also a vector. It points into a certain direction. It has a quantity, a value, and it has a direction to it. Okay, and the direction of this L you can determine with your right-hand rule. Okay, so if this particle here is moving along P in that direction, and R moves from 0 to this way here, then the angular momentum is sticking up. That's the thumb. Okay, so if you have a particle that moves around in a circle like that, then there's the angular momentum of that is pointing up. That's the direction of the angular momentum. Different from linear momentum, right? So that is the angular momentum. It actually points along z. If the particle moves in x, y, then the angular momentum points along z. It can point up. It can also point down if the particle spins the other way. because then the direction of P flips. How do I calculate this vector product? This is how you do it, right? Hopefully it looks somewhat familiar from vector calculus. The I, J, and K are just the directions along X, Y, and Z. And then the X, Y, and Z are the values of R along the coordinates. And Px, Py, Pz are the values of the momentum along the Cartesian coordinates. I can write it out, okay? So Lz, if it points along Lz, okay, then I basically select the K part, and the K part is X times Py minus Y times Px. Okay, hopefully you see that, because what I'm going to do is this guy times this guy minus this guy times that guy. Okay, that's the contribution along K, which is here, this direction. Now, this is, again, classical. This is very general. We haven't done anything quantum yet, but now I'm going to take the quantum leap. Okay? I'm going to now turn those things into operators. Okay, so I have now my angular momentum operator, which I call LZ, the little hat, because I'm concerned with the momentum, the angular momentum that's directed along the z-axis. I see here I have the operator x, and then py minus y px. What do these things look like? Well, I know that from a bunch of lectures ago. I can just fill it out. The x is just multiplication by x. The py is h bar over I, then the first order derivative with respect to y, and then minus y h bar over I, first order derivative with respect to x, because that is what px is. So that looks somewhat unpleasant. I have two derivatives, one to y, one to x, but again, I can use polar coordinates. And we don't have to do it ourselves, but I can tell you that if you rewrite this in terms of polar coordinates, and there's no changes along r, which is the case, then this simply looks like this. H bar over I equals the first order derivative with respect to phi. Okay, so the only thing I've done is I've rewritten the top in terms of polar coordinates, cross out all first order derivatives with respect to r, because those are 0, and I'm left with just this term. It looks pretty clean. H bar over I, and then the first order derivative with respect to phi. This looks just like momentum in terms of x, but now the phi is taking the place of x. Okay? So very similar. So now let's see what happens if I operate with this momentum operator, this angular momentum operator, onto my function. Because I would like to know what is the angular momentum if the electron occupies that wave function. Okay, so here's my wave function. I'm going to take just the complex exponent with the plus part, and I'm going to see what happens. If I take it with the negative sign, then the answer is going to be the same with the negative sign. So let's just solve this problem here and see what we get. So what I want is, I want to operate with this angular momentum operator onto my wave function and see what I'm getting. There it is. That is the form of the operator, h bar over I, and then the first order derivative with respect to the wave function. I see I can take simply the first order derivative of the wave function, which depends on phi, which generates the wave function again, times a constant. Okay? And the constant is going to be IML, times what I had before, h bar over I, that stays, and then the wave function again, which is simply n times the complex exponent. So the i's, the little i's, the complex numbers, as the prefactors, they will cancel out. You can see that, there's one numerator and one denominator. So what I'm getting is ml, h bar, and then the wave function again. Okay? And that means that this wave function is an eigenfunction of the angular momentum operator, because this is an eigenvalue equation. And then the eigenvalues are ml times h bar. Okay, so the value of angular momentum along the z-axis is ml times h bar. It's just a constant times h bar. It's just a constant times h bar. If ml equals 1, then the value of angular momentum along the z-axis is just h bar. Now h bar is a tiny number, right? So it's a very tiny value. There's also something else I can say about h bar. H bar has the units of angular momentum. So you can interpret h bar in a variety of ways. The constant of Planck divided by 2 pi is h bar. You can interpret it in a variety of ways. But one way in which you can interpret it, that it actually tells me something about the angular momentum of my particle, of my object. It quantizes angular momenta in quantities of h bar. Okay, I'll leave it at that, folks. Let you go.